Alrighty, this is project 2 and it's on Kirchhoff's laws and input and output modeling. So for some housekeeping stuff, just to keep us on track, we're going to go through some circuit analysis. That's the actual project. We're going to attempt to solve the Wheatstone bridge circuit by balancing the voltage using Kirchhoff's voltage law, Kirchhoff's current law, and Ohm's law to convert back and forth from voltage to current times resistance. Then we're going to look in section B at input and output modeling. We're going to look at a different topic in the world and see how it relates back to the electricity example in the project. And then part C, summary and reflection, both on my topic I picked plus this here. Let's get started. So we're given the Wheatstone bridge circuit. We need to rewrite it into a user-friendly format. So this is what we'll be using for the rest of this project over here on the right. And we're going to choose 4 distinct resistances between 5 and 10 ohms. Okay, well, I just chose 6, 7, 8, and 9 because that seemed pretty easy to me. And I wrote them out, 1, 2, 3, 4 is 6, 7, 8, 9. So that's hopefully going to help us stay on track. When V out is disconnected, there are 2 current cycles. You see I1 and I2. If V out was connected, the entire problem would be completely different. You would have I1, I2, and I3, but you only have 2 rooms here, not 3 rooms, because this is disconnected. So that makes our lives a little bit easier. It means that there are just 2 equations. We're going to actually use KVL. This really confused me because we're dealing with current here in amps. All these I's represent amps. But this V here stands for volts, so we're using the volts law, but we're in amps. Of course, we use Ohm's law to convert back and forth. Initially, that really threw me off. It took me quite a bit to figure that one out. Yeah, so we get our 2 equations here all laid out. Let's simplify those and put them into a matrix. So we expanded, we simplified, so these ones look a lot more like the ones you get in a textbook. And then we can throw them into a matrix here on the left. And then we can put it into reduced row echelon form and get our amps. So our amps for circuit, or I guess loop 1 of the circuit is 1.63. And for loop 2 is 0.92 amps. Our determinant here, if you take a look at our first matrix before we reduce it, it's 221. Yeah, I didn't really find the determinant to be useful at all. I don't think we need to bother calculating it, honestly, because we know that we're going to get answers in this problem, or they wouldn't have us bother doing this problem for a project. Because it's not 0, we know that there are not infinitely many solutions. And we do know that there are more than 0 solutions, obviously. Because there are 2 rows here, and they both reduce correctly, there aren't like a bunch of zeros in one of these rows, then we get 2 solutions. The determinant also doesn't necessarily say anything about uniqueness, because it is not the partial derivative, which is used to determine uniqueness. So I could be misunderstanding the determinant a little bit, but I did not find it to be useful at all, really, in this project. But yeah, there it is. Okay, so we got the loop currents for loop 1 and loop 2. Let's use those to solve for the branch currents. So each resistor essentially is going to be a branch. If V out was connected, there would be 4, 5 branches, maybe 6, depending on how you figure it, or 5 and 6 would be equal, I'm not exactly sure. But because V out is disconnected, you end up still having 4 branches, right? They're separated by these nodes here in the middle. But, I mean, because there's only 1 room here and 1 room here, you have I1 and I2, these two branches and these 2 branches are going to be the same. I solved for them down here, of course, and they literally equal the same thing. So, yeah, I guess that's nice. It's just how it ended up working out. Now that we have the branch circuits, we can use the resistors to convert back to volts to see the change in voltage across the resistors. Okay, so these are all going to be measured at the node points, right? N4 is obviously 12 volts. And then across this resistor, there's going to be a voltage drop. Take this voltage here, go across this resistor, there's going to be another voltage drop. And same thing over here, right? So when I was done with the whole project, I realized I didn't actually need to solve for N2 or N5, but I did anyway because I didn't realize I didn't need to solve for them when I solved for them. So that's why they're here, but they're kind of useless. You can ignore them. Mainly what we're looking at here is the V out. So that's going to be N3 versus N1. Are they equal? Because if they're equal, then V out's going to be 0, because V out is the change in voltage between those 2 points, right? So yeah, let's take a look and see what's the deal, because they're obviously not equal. Yeah, so you got 5.61 volts minus 6.48 volts. They're not equal. If we go back to the previous slide, actually, something to note here. This here number is the actual measured voltage if you were to use a multimeter. So if you go, the voltage you're calculating is actually the voltage drop, if I understand this math correctly. It's a voltage dropped from whatever the previous voltage was, right? So from N3 to N2, the voltage drop at N2 that you calculate is going to be subtracted from whatever real voltage was at N3 previously. So if we do that, right, N4 is going to be 12 volts, no resistors. And then we go down to N3, it's going to have this resistance, right? It's going to drop this many volts, and this is how many volts here, 5.61 volts that it's going to actually give us if we measure it. Then we go through resistor 3 to N2, and it's going to drop 5.68 volts, giving us only 0.71 volts to actually use at the end here at node 2. Yeah, so this is supposed to be 0, and it's not. There's a way to fix that, though. What you can do is use the given equation here in the project and reverse engineer it to solve for R1. Well, then you plug in all your numbers for your other resistors, and you can say, see here, my R1 should be 14.875 ohms. So then you redo the entire problem with that as your new R1. And I literally kept the same screenshot and just chopped this off to show that that's the only thing I changed. We go back through here, you know, we get our two equations, we distribute everything, we simplify it, then we throw it in a matrix. The only value that changed is this one right here. It used to be a 35, now it's a 38.875. Solve it using throw it into reduced row echelon form. Previously we had this here value, now we have these values. They're both slightly lower. The determinant is greater. It means the same thing as last time, which isn't a whole lot. I did not find it to be useful at all in this project, so I don't know why we're bothering to do anything with it, but it's not really that related. Like, I mean, sure, it tells you if something exists or not, right? But like, I could just do this, and since I need to do that anyway to get my answers, then yeah. Anyway, I did not find it helpful at all. Yeah, so we solve for those loop currents, right? Right here. Those are our new loop currents. Now we can solve for our new branch currents right here. They're both a little bit lower too. But we're really interested in these nodes here, these node voltages, and I solved for all of them. I didn't need to. It's the exact same format as last time. We're particularly interested in N1 and N2. So that's this guy here and this guy here that are not the same. That's a bad thing because they should be the same. They should equal 0, but they don't. Yeah. That's really weird because this is the way that you're supposed to do it. You solve for R1. You use your new R1 to solve for all these other things, your current and then your node voltage. But it didn't work for me. So I tried to backtrack a little bit, figure out what was going on, but I mean, when I got to this point and I figured out E equaled 0, I was 7 hours into the project and I'm like, I have got to get done. I can't redo the entire project just because my data didn't work out. Like physics lab, right? You can't redo all your experiments because your data wasn't accurate. Well, it's just the data you got, so you have to show it. Yeah, so now we're on to part B here. We want to look at more of a real world example. So back in 1900, ranchers used ditch boxes to measure how much water they're getting on their crops. These boxes act like a resistor. They're resisting water, where water would be electricity. The ditch box is the resistor. Each rancher had a legal limit of water. Of course, in the dry season, you want more water because your crops are dry and your animals are thirsty, whatever. They would open their ditch boxes all the way, reducing the resistance. And then, of course, there's less water for the next guy. An example drawn out here. I actually used AI to draw this out for me because I didn't want to waste time trying to type all those numbers out, but I told it to make a circuit using ditch box analogous to electricity, and it came out pretty much what I was expecting, and it works for our purposes here. It's an example of a linear system, much like the ones used in electricity that we previously looked at in the project. In a circuit form with ranch A, that's RA right here, ranch B right there. Two junction boxes, those are our ditch boxes that we just saw in the previous picture, and an overflow bypass right here. So this is all dependent on the season, right? So we have water coming down the main canal. It's flowing to the right. First, it's going to come down R1. It's going to hit junction box 1, and if it's closed in the winter, he doesn't want water. All that water is going to go straight over to junction box 2. If junction box 2 is closed because it's also winter, same season over there as it is over here, and only a mile apart, whatever. Well, all that water is going to flow right back up the bypass overflow, and it's going to flow back in the main canal to the next rancher over here on the right that's not pictured. Well, something really interesting here to take note is all these R's. So these ditches are actually R values. You think of that as a resistor. Well, that's because it is a resistor in a way. It's actually absorbing water into the ground, and of course the water is also being evaporated by the sun. So whatever water you have here is going to be more than the water you have here, just because of the nature of water. It's gonna evaporate, and maybe it might not be a whole lot, but it's going to be some that evaporates. So yeah, in the summertime it's completely different. It's not even a real circuit in the summertime because this overflow bypass is going to be completely dry. All this water is coming down R1. This guy has his box open all the way, trying to get as much water as he can. Well, whatever's left is going here to ranch B. He's getting as much as he can, right? Probably taking more than the legal limit because he doesn't want his alfalfa to die. So they're both taking as much as they can. No water is coming back here. So all this water in the main canal, it's just going to be less and less to the next guy. Yeah, so in summary, KVL, KCL, essentially, what goes in must come out. And in my example, it's like there's an asterisk and then get absorbed, right? Because obviously the same amount of water coming in is not the same amount of water going out. Some of it's getting absorbed. Now, in electricity, if we're going to talk power lines, over a long length of wire, there's some serious current loss. What they do, because it's measured in watts, is volts times current. What they do is they lower the current and up the volts, right? So that you're not going to experience so much current loss. There's less current to lose if it's lower and there's higher volts. But that's the same amount of power, so... yeah, a little bit more reflection. I think the reason I didn't get 0 on the volts out is because I used too many variables with the letters and the numbers, and I probably just swapped one somewhere. I didn't really do the entire thing, so I don't actually know where that was, but that's my guess. Yeah. I also thought it was pretty neat. You don't need a multimeter, but I also thought that it would take I mean, I'd spend an hour at tops on this project if I had a multimeter and I just built the circuit with some wires, right? Just measured it a couple times and be like, oh, this is V out, and let me change these resistors so V out equals 0 instead of doing all the math. But yeah, it's neat. You can do it both ways. Yeah, so my application with the ditch box is related back to the electricity because it used a form of resistors, which is, of course, the ditch box is resisting flow, and even the ditches themselves a little bit, and also use a power source or water in this case. Yeah, a couple discussion questions to end this project off. Are the assumptions reasonable behind Kirchhoff's laws? So yeah, of course it has to assume that you're not losing any voltage or whatever your or current in some cases, whatever you're measuring, you can't be losing any of it or your calculations are going to be thrown off. For computers, I think this makes sense. You got your motherboard, everything's so close together, it's so small. Your current loss over a long piece of wire is not something to worry about. For like PGE, power company, I don't think it's going to be as useful because these guys use super long distance stuff. You're gonna lose current. I think it's reasonable assumption that nothing's getting lost in maybe a computer, but yeah, you're losing current in these long wires. It's just how it works. It's not as obvious as water evaporating because you can't see that there's less, but you can measure it. How similar was my selected topic? I think it was decently similar. I selected it actually. I always really enjoyed reading those old Western books by like Ralph Moody and stuff where they're shooting each other with guns over the ditch water because they need the water to survive. So yeah, it's kind of interesting. I had AI make the diagram for me and it resembled a circuit, so I was like, okay, this works. Yeah, it was relatively similar. We had things that provided resistance to the circuit, and you had the source of water, right? So, some practical restrictions. Well, I mean, we just kind of went over that. Distance, obviously, it only works if your distance is close enough together. If you have a really far distance, your power, your current loss, you got water evaporating. Also, the season, and this is even true for power lines because sometimes, of course, they're not going to want to send as many watts down a power line if it's touching a tree in the middle of summer. They don't want the tree to catch fire. They don't want the water to evaporate in the summer either, but that's gonna change everything. What sizes in order to magnitude? So in practical applications. So yeah, PGE, of course, their stuff's in kilowatt per hour. That's how they charge you, right? So assume that's kilowatt, and you have kilovolt and kiloamp to get kilowatt or something like that, right? Kilo means thousand, so I mean that thousands of watts. I mean that's a lot. That's a lot of watts. Irrigation ditch in my example, that's going to be in inches per acre. Bigger farmers, bigger ranchers, they get more inches of water at their ditch box. That's in height, right? At your ditch box, they're going to get more water legally because they have more land that they need to. They need more water on their land because they have more land. Yeah, so that's going to be in inches. Yeah, I think that's pretty much everything for this project. Yeah, thanks for watching.